Hello again. This is Lesson 29, Sequences and Series. This is probably something you have not seen before in an Algebra 1 class, and it's even possible you will not see it in an Algebra 2 class, although I believe an introduction to sequences and series is necessary, especially in this world of computers and programmable calculators. It's a matter of using sequences and series in programs on computers and in calculators to solve serious problems. In fact, once we talk about sequences and series, you'll see how possibly they fit together with the recursive functions we talked about recently. In this lesson, we're going to first talk about summation notation, which is something, again, you may have seen, but if you haven't, you'll have seen it now and you'll understand it. It's really simple, just a way of mathematically symbolizing addition. Then we're going to look at arithmetic sequences and arithmetic series, geometric sequences, a brief look at geometric series, and the infinite geometric series. And that should cover everything you need to know at this time. There'll be more of this if you take calculus. There's a couple of chapters on sequences and series that are vital in first-year calculus. But that's for a later date. Right now, let's talk about the summation notation. And if we look at the first visual, you could see a symbol that kind of looks like a sideways M or W or a very strange looking E. That is the Greek letter sigma. That is the printed sigma. It's the Greek letter. It kind of stands for S, similar to S in our alphabet. And that symbology is read the sum from n equals 1 to 4 of 2n plus 1. Now, what does that mean? Let's examine each part of that symbology. The sigma means sum or add. Remember, the sum is the answer to an addition problem. The n at the bottom of the sigma tells us what we're going to use as the indexing variable. That is, what we're going to use to create the sequence that we're going to add up here. N. And then n equals 1 means we're going to start with n of 1. N could start at 0, n can start at 2, or even 17 in some cases. And then the number at the top of the sigma, in this case the 4, is the number at which we stop. So n goes from 1 to 4. N equals 1, n equals 2, n equals 3, and n equals 4. Notice, these are the counting numbers. We're not going to talk about any negative numbers and no fractional numbers for our indexing variable, in this case n. Sometimes we use I or j as an indexing variable. The 2n plus 1, you'll notice, is in parentheses, which means we're going to take the indexing variable, n, replace it with 1, and then 2, and then 3, and then 4, and get 4 numbers, and add them up. And at the bottom of the visual, you notice we've taken n equal 1. 2 times 1 plus 1 is 3, and there's your 3. We've replaced n with 2. 2 times 2 plus 1 is 5. And we replaced n with 3. 2 times 3 plus 1 is 7. And we replaced n with 4. 2 times 4 plus 1 is 9. 3 plus 5 plus 7 plus 9, the sum of those four terms is 24, which is the answer to our summation problem. And again, we will use the summation symbol in sequences and series, so I wanted to introduce it to you at this point in time. It's pretty simple. It just simply means an easy way of saying add these things up, okay? Now, let's take a look at the arithmetic sequence. What is an arithmetic sequence? And again, you should notice that when you use the word arithmetic as a noun, excuse me, it's a arithmetic. When it's used as an adjective, it's arithmetic. So let's look at our next visual, which is the arithmetic sequence. Notice it says arithmetic sequence, common difference. An arithmetic sequence, the difference between two succeeding terms is always the same. So, for example, the counting numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., is an arithmetic sequence, since we add 1 to the previous number to get the next counting number. This is an arithmetic sequence, 1, 2, 3, 4, dot, dot, dot. In fact, that represents the counting numbers. The dot, dot, dot means and so on and so forth, forever and forever. The next sequence that's listed, highlighted on your visual, is -8, -3, 2, 7, 12, ... What is the common difference there? Well, to find the common difference, you can either say, what do I have to add to one term to get the next term, or let's take one term and subtract from it the previous term. Let's do it both ways. Let's take -8. What do I have to add to -8 to make it -3? Well, I believe that would be -5. No, it would be +5, because obviously from -8 to -3, we're going up the number line, and therefore we're adding a positive number. The way to check that is to say, hey, if I add 5 to -3, do I get 2? Yes, I do. And when I add 5 to 2, do I get 7? Indeed. And of course, 5 plus 7 gives us 12. What would the next term be? Well, since the common difference is 5, we're going to add 5 to 12 and get 17. Now, let's go back and investigate the same sequence, the -8, -3, 2, 7, 12 sequence, using subtraction. If I wanted to find the common difference by using subtraction, I could say -3 minus a -8. Subtracting a -8 is the same as adding a +8. -3 plus 8 is 5. So either way, we get the common difference of 5. The important thing is, once you get the common difference, check to see that indeed it is a common difference for all the terms indicated. Because it could be pretty sneaky if the first 3 or 4 terms look like an arithmetic sequence and then it changed. And I wouldn't do that to you, but someplace on a test you might see that. It's always important to investigate and verify that indeed this is an arithmetic sequence. And the last line in that visual, another arithmetic sequence, 9, 6, 3, 0, -3. Notice the terms are getting smaller, or lesser, we should say. And therefore it means that what we're adding is a negative number. You could say, well, we're subtracting. Either way, it's the same thing. And the common difference in that last sequence is -3. We add -3 to 9, we get 6. We add -3 to 6, we get 3, and so on and so forth. In fact, I ask you what would be the next term after -3 in this sequence. And you should say, well, -3 plus the common difference, -3, is -6. If you said that, you would be absolutely right. Now let's take a look at some symbology for use in arithmetic sequences. And that's our next visual. It shows us that we use A to indicate the term. And each term A has a little number subscripted, that is, below it. It's called a subscript, an indexing number. The first A is A1, the second A is A2, etc. So A1 is the first term. Very, very important, because as we saw in recursive functions, if we know the first term and we have a rule, we can get the second term. Same idea here. We're going to be very, very important to know the first term. Now, A sub n means the nth term. If n was 12, then A sub n would be the 12th term. If n was 100, A sub n would be the 100th term. And then D, lowercase d, is the common difference. What we add to A1 to get A2. What we add to A2 to get A3. And notice it shows you that on the last 3 lines in this visual. A2 is A1 plus D. Take the first term, add the common difference. A3 is A1 plus D, which gets us the second term, plus another D, which gets us to the third term. And A4 is A1 plus D plus D plus D. Looking at those 3 definitions, if you will, notice there's something common. Can you see a formula for finding A sub n? Because you'll notice that in every case, the number of common differences, the number of D's we added, is always 1 less than the little subscripted number under the A. That is, to find A3, we took A1 plus 2 D's. A4, we took A1 plus 3 D's. How about A13? If we wanted to find A13, we take A1 plus 12 D's. Okay, now I want to find A sub n. Let's go to the board and take a look. Well, we know we start with A sub 1. And we know that we're going to add a number of D's, a number of the common difference. And rather than adding D plus D plus D plus D, we are going to multiply it by the number of D's. We saw that to get A sub 4, we added 3 D's. To get A sub 13, we added 12. One less than this number here. That is, what's in parentheses is one less than this, and that is very simple to write. That's n minus 1. And that is your formula in arithmetic sequences for finding the nth term. So in other words, practical use of this, let's assume that you had a salary structure where every 6 months hourly employees received the same increase. Let's say they received a dime an hour, 10 cents an hour increase every 6 months. Well, how much money would someone be making per hour after, let's say, 4 years? That would be 4 6-month periods. After eight raises. Well, all we'd say is A1 is their starting salary, hourly rate. The difference is 10 cents. And n minus 1 would be the 7 raises they would have received after 8 periods. Okay, so 7 times the common difference. In other words, they'd be getting 70 cents an hour more than when they started. And there are many real-world situations that approximate this arithmetic sequence. Another word, by the way, for sequence is progression. Sometimes this is called an arithmetic progression. Let's look at an example of finding the nth term in an arithmetic sequence. The next visual shows us that. We are given the sequence 7, 11, 15, ... which means whatever is happening with 7, 11, and 15, that sequence continues. The question, is it arithmetic? Is there a common difference? Well, let's see. What do I have to add to 7 to make 11? 4. What do I add to 11 to make 15? Also 4. Yes, there's a common difference. You'll note it takes at least 3 terms to determine the nature of a sequence. We're asked to find the 21st term. Why? Because that's the question. In the real-world situation, this could very well be something that happens in the 21st day or the 21st item in the sequence is important to us. The initial value, A1, is 7, again, from the original information we were given. The common difference, D, is 4. We've already determined that. We write it in. And N is 21, the 21st term. Using our formula, A sub N equals 7 plus 20 times 4. The 7 is A sub 1, the 20 is 21 minus 1, n minus 1, and the 4 is the common difference. 20 times 4 is 80, plus 7 is 87. So the 21st term in this sequence is 87. Just like when we worked with recursive functions, we wanted some way to find out something without having to go through every single number as we went through the recursive function. Same thing here. We could have found the 21st term by continually adding 4. To 15, we get the 4th term, which is 19, plus 4 is 23. But this is much nicer. Imagine if you had to find the 1,000th term. Would you want to, write down all those 1,000 terms? Much easier to use this method, a simple formula to find the nth term in an arithmetic sequence. Okay, what is this thing called a series? And no, it really has nothing to do with the World Series. A series is a mathematical term for the sum of the terms in a sequence. Okay? Sometimes, for example, you could have a sequence, let's say in a business situation, where your sequence is the number of items sold per day or per hour or per week. And if there was something approximating an arithmetic sequence, that would mean each day you sold some more than the previous day, and the amount you sold more than the previous day was the same from day to day. Well, the series would be the sum of those sales or the total sales for that period of time. So the sum or series can be very useful when the items in the sequence need to be added up, when there's a cumulative effect. Okay? What is a series? Again, how would we symbolize it? Well, let's look at the next visual, which talks about or shows us the definition of series. Again, sometimes you need to see it written out as well as hear it from my lips. The sum of the terms of a sequence. How many terms? all the terms, all the n terms. And the symbology, again, the Greek letter sigma, which we introduced earlier, the sum from I, in this case the indexing variable I goes from 1 to n of a sub I. A sub I is the ith term of a sequence. So if I was 1, a sub 1 would be the first term. If I was 17, a sub 17 would be the 17th term. And when I is n, it's the nth term. And here we're summing up the first n terms of a sequence. How would we do that? Well, let's take a look at a simple arithmetic sequence in the next visual. We have a sequence that is exactly 6 terms. Not all sequences have to go on forever and ever. This one stops after 6 terms. We have negative 11, negative 5, 1, 7, 13, and 19. What is the first thing I should do? The first thing I should do is verify that this is an arithmetic sequence by finding the common difference. What is the common difference? Well, let's see. The terms are getting more positive, which means I'm increasing, which means my common difference is a positive number. I'm adding a positive number. And what do I have to add to negative 11 to get negative 5? I believe 6. Negative 5 plus 6 is 1. 1 plus 6 is 7. 7 plus 6 is 13. And 13 plus 6 is 19. So we can see that this is an arithmetic sequence. What I've done for you here is something that was discovered by a very famous mathematician I'll talk about shortly. Let me talk about it first before I talk about what I've done here. Many, many years ago, there was a mathematician whose name was Gauss. Gauss, the story goes, was a very brilliant and precocious child in his classroom. And the teacher was one day trying to get Gauss to just not answer any questions, not ask any questions, just go away, keep him busy while he could teach the rest of the class. So he gave Gauss a problem to do. Gauss was quite young. I mean, the stories vary. I've heard as young as, let's say, 6 or 8 years old. But he was a young child in school. And the teacher said, told Mr. Gauss to go ahead and add up all the numbers from 1 to 100. And the teacher, thinking that this was a really good trick, because Gauss would say 1 plus 2 is 3, plus 3, and it would take him a while. Even if he can add fairly quickly, it would take him a while. He'd get the other students started on some other lesson. And immediately Gauss put his head down, supposedly, and looked up and said, 5,050. The teacher was just utterly aghast. He said, how did you do that? You must have worked at this before. It's impossible if you add those numbers up so quickly. And what Gauss said is he hadn't added the numbers up. He recognized that there were 100 numbers, and that the first one and the last 100 added up to 101. And the next number, 2, and the next to last number, 99, added up to 101. And 3 plus 98, and 4 plus 97. In fact, there were 50 pairs of numbers, each which added up to 101. And 50 times 101 is 5,050. That's it. Well, of course, this was utterly amazing, which proved the level of intelligence that Gauss had. And going back to our visual, this is an application of that. We know that negative 11 plus 19, the first and the last, equal 8. And negative 5 plus 13 equal 8, and 1 plus 7, the middle two terms, equal 8. We have 3 pairs times 8, each pair adds up to 8, equals 24. So, from this, we can get a formula for adding up the terms of an arithmetic sequence. Let's go to the board. We'll leave this up here because this is the formula for the nth term. Now I want the formula for the sum of n terms of an arithmetic sequence. Well, according to Mr. Gauss, or Herr Gauss, he was German, let's take the first term and the last term, in this case a sub n, and add them up. And then multiply that by the number of pairs of terms. Okay. Well, there are n terms, and half that number would be the pairs. So n over 2. You say, wait a second, what if we have an odd number of terms? This would be a fractional number, something and a half. Well, if you had an odd number of terms, then, quite frankly, you prove this, both of these would be odd or both of these would be even, and therefore the sum of 2 odds or the sum of 2 evens would be even, and the 2 would cancel out. Either way, if the sequence is whole numbers, or at least integers, then the sum will be an integer. And of course, this is the sum from I equals 1 to n of this arithmetic sequence. This only works for arithmetic sequences because in the arithmetic sequence, because of this common difference, when you take the second term, a sub 2, that equals a sub 1 plus d, and the next to last term, a sub n minus 1, equals the last term minus d. One difference less. When you add those up, you get the second plus the next to last term. You get the same as the first plus the last term. So that's the reason. There's no magic. And like I say, Gauss explained it very well. Hopefully you understand it. So here's your formula for the nth term of an arithmetic sequence, and here's your formula for a sum. These are two things you should know. Let's use that over here. I'm going to erase this now. If you haven't copied it, stop the tape and rewind it. Copy it down. Let's go ahead and do one. Let's see. We have, let's first look at the visual, which will give us the problem. Then we'll go back to the board to work the problem. The visual says here 17, 12, 7, ... Find the sum of the first 12 terms. Okay? And therefore, symbolically, the sum as I goes from 1 to 12 of a sub I. The first term is 17. The common difference is negative 5. I add a negative 5, and to 17 I get 12. I add a negative 5 to 12, I get 7. And the number of terms is 12. Remember, to work that formula, I need to get the 12th term, which I don't have yet. So at the bottom of this visual, we get the 12th term, which you can see, using the formula, we get negative 38. Now we go to the board. And now we say that this sum, and I'll just use the Greek letter sigma, is going to be the number of terms, 12 over 2, times the first term, which is 17, plus the second term, plus a negative 38. And that turns out to be 6 times minus 21. And therefore, the sum of all of these 12 terms is negative 126. And in fact, if you went back to the original sequence, although you didn't see any negative numbers, you recognize that indeed, if we add negative 5 to 7, it's 2, and all the numbers after that will be negative, getting more and more negative each time. So indeed, we have a whole lot of negative numbers, which would cancel out the small number of positive numbers, giving us a negative sum. Let's take a look at the next visual. And the next visual tells us about a geometric sequence. Geometric sequences have a common ratio. Instead of adding a term, we multiply a term. And it gives us some examples. In the first geometric sequence, which is highlighted, 5, 10, etc., we see we multiply by 2. In the next geometric sequence, we multiply by a negative, negative 3. Notice by multiplying by a negative, the signs of the terms alternate, negative, positive, negative, positive. And in the third sequence that is shown, again, a geometric sequence, because we're multiplying by a common ratio, and that common ratio is a half. So in other words, we can't have fractional multipliers, just as we could have negative common differences. All right, in the bottom line, which is highlighted on the visual, it tells you that R is the symbol for a common ratio. The next visual shows us that we can, just as we found the terms of the arithmetic sequence in terms of D, we can find the terms of the geometric sequence in terms of R. A2 is the first term, A1 times R. A3 is A1 times R, and so on. As you can see, A5 is A1 times R times R times R times R. The next visual takes those exact same statements and shows us that A3 is equal to A1 times R squared. That is R times R. And A4 is equal to A1 times R to the third power. And A5 is equal to A1 times R to the fourth power. Well, what would A sub n be? It looks like the power is 1 less than the index on the variable. And just like the number of common difference we had, it was 1 less than that indexing number. So let's go to the easel and write out that formula. It would seem that the nth term for a geometric sequence, and this is geometric, would be A, or A1 if you like, times R to the n minus 1 power. Now, in some books, in your book is possibly one of these, they sometimes use G for the terms in a geometric sequence, the A for the terms in an arithmetic sequence. Many books use A for all terms of any sequences. Okay, let's go to the next visual, which uses this formula to find the 11th term of a geometric sequence. How do we know it's geometric? 3, 6, 12. Well, what times 3 is 6? 2. Is 2 times 6 12? Yes. What would the next term be? 2 times 12 would be 24. It says find the 11th term. Again, A1 is 3, R is 2, N is 11, the 11th term. And let's see, the 11th term, according to our formula, is the first term, 3, times the common ratio raised to the n minus 1 power, or 3 times 2 to the 10th. Do we multiply 3 times 2 first, or we raise 2 to the power first? Well, we always exponentiate before we multiply and divide, therefore 2 to the 10th, which is 1,024. Then we multiply by 3, giving us this 3,072. Okay, let's take a look at the next visual, which looks a little busy. And it's the kind of thing I will briefly explain. You might want to go back and take a look at it at a later time and go over it. Basically, it's one of these things I like to do in this series, which is to show you why something works. We want to find the sum of a geometric sequence. And we use a little trick. On the first line, we see that the sum is equal to A1 plus A1R plus A1R squared, dot, 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 plus A1 times R to the n minus 1. That is the first n terms that we're adding up. We then, and here's the tricky part, we take that same sum and we multiply it by R. And we multiply each term by R. I mean, both sides of the equation are multiplied by R. And we get A1R plus A1R squared plus A1R cubed, dot, 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 dot. The last term, of course, would be A1R to the nth. On the third line, which is highlighted on your visual, we subtract the sum minus R times the sum. And the terms with the R in it, and the R squared, and the R cubed, dot, 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 always the R n minus 1 term, all cancel out. They're the same when you subtract. Things are the same. They cancel out. All we're left with is A1 minus A1 R sub n. The very first term in the sum, and the very last term when we multiplied the sum by R. And we then factor out 1 minus R, leaving us with the bottom line, which, even if you don't follow it, or you don't say, I don't like tricks, that is the formula for finding the sum of the first n terms of a geometric sequence. Okay? We're not going to spend any time on this as far as sums. We're going to calculate it. It's easy to figure out powers. I want to show you a very special circumstance of the geometric sequence, one that comes in quite useful, especially for those of you who will be taking calculus later on. You go back and you'll say, gee whiz, here's something we can understand. It's fairly difficult in calculus, made easier by something we learned in Algebra 2. So let's go to the board and look at the infinite geometric sequence. What does that mean? Well, let's first erase this stuff. The infinite geometric sequence is simply a geometric sequence that goes on forever and ever. To be useful to us, we have to have something where the common ratio, what we multiply each term by, is less than 1, or if it's negative, it's between -1 and 0. In other words, we must have something whose absolute value is less than 1, closer to 0 than 1 or -1 is. So, for example, here is a sequence of that type. We have 1, 1/2. We multiply by 1/2 each time, so it has a common ratio. That is, R is 1/2. It goes on forever and ever. The numbers are getting smaller and smaller and smaller. What happens as n goes to infinity? As n gets larger and larger. Here's n is 1, 2, 3, 4. What happens way out here? Okay, what happens is that we're going towards 0. Eventually, these terms get so small, they might as well be 0. They never actually reach 0 because infinite means without end. Okay? And what do? Well, our R to the n would be 1/2 to the infinity power, in effect. I mean, really, what it means is what's happening as n gets very, very large, 1/2 is getting to the n power is getting smaller and smaller, and it's a word we call the limit. The limit of that is 0. So what we wind up with is our sum, which we said was a1 times 1 minus r to the n over 1 minus r. This is 0 because, I should say it, this is 1. 1 minus 0 is 1, and 1 times anything is itself. So we're left with a1 over 1 minus r, which means we don't have to go through this whole mess. We want to find the sum of this sequence. All we've got to do is take the first term, which is 1, and subtract the common ratio, which in this case is 1/2, from 1. This 1 is the first term. This is just the number 1. And we get 1 over 1/2, which is 2. If you add these up, 1 plus 1/2 is 1 1/2, plus 1/4 is 1 3/4. You'll see you're getting closer and closer and closer. You actually never get to 2, but so close you could say its limit is 2. Okay? And therefore, this works again as long as r, the common ratio, is a number between -1 and 1. It can't be 1 or -1. It has to be a positive or negative proper fraction. Of course, it can't be 0 because that's kind of silly. And this formula right here, the sum for an infinite geometric sequence is a1, the first term, over 1 minus r. Well, that just about takes us through sequences and series in terms of what you need to know for Algebra 2. We've looked at the symbology of sigma, we've looked at the arithmetic sequence, we've looked at the geometric sequence, how to find the nth term, and how to find the series. That is the sum of those terms. In our next lesson, and our final lesson in this series, we will take a look at an introduction to trigonometry. We'll see you shortly.